This is a pre-lab discussion for experiment 19 in chemistry 1B, and experiment 19 is about corrosion and electrolytic cells. So this is broken into two parts. The first part is corrosion, so I'll discuss that first. So specifically, we're going to look at the corrosion of iron. So for the corrosion of iron, there's two things that happens. One is that iron is oxidized. And of course, if something is oxidized, something is reduced. They go together. So in the corrosion process, oxygen is reduced. So for the oxidation of iron, it actually occurs in two different steps for corrosion. And the first is that the iron solid is oxidized to iron 2 plus. And so, of course, it lost 2 electrons. And then the iron 2 plus is then oxidized to iron 3. So it occurs in two steps in the actual corrosion process. In this experiment, we can identify that iron 2 plus was produced by adding a color indicator, right? So we could detect the formation of the iron 2 using an indicator, and in this case, that indicator is a complex ion, and that is hexacyanoferrate 3. And so that reacts with iron 2 in the process I'm writing here. So 3 iron 2 ions react with 2 of the complex ions, and that forms a complex that I'm writing here. So it's a complex with iron 2 and then the complex ion. And overall, this complex is a blue color. So if you see blue in your systems in this experiment, what that is telling you is that iron has been oxidized, right? So iron's been oxidized to iron 2. So in the real process of the corrosion of iron, oxygen is reduced in the presence of acid. We're not going to add any acid here, but we do have water. So oxygen gas plus 2 moles of water plus 4 electrons gives us 4 hydroxides in this reduction of O2. And we should know that we can add a color indicator to show that hydroxide's produced, because this will turn pink with the indicator phenolphthalein. We should know that from our titration labs, right? That in the presence of hydroxide with phenolphthalein, we get a pink color. So our two color indicators are blue means iron is oxidized to iron 2 plus, and pink means that oxygen is reduced, in this case, to hydroxide. So blue means iron is oxidized, and pink means oxygen is reduced. Those are two key points to keep in mind when you're observing your corrosion systems. And those are what I'm going to talk about next. So we're actually going to set up 4 different systems for the corrosion process. So we are going to investigate, like I said, 4 nail systems, and the nails are iron nails. So the first is just one plain iron nail. The second is an iron nail with a zinc metal piece on it. Third is an iron nail with a copper metal piece on it. And the fourth is an iron nail with both copper and zinc metal on it. Keep in mind that oxidation and reduction occur together. So what that means is that if something is reduced, then that means that something had to be oxidized. Right? So if you see pink in your test tube, that means oxygen is reduced. Something must have been oxidized. If it's blue, that means iron. If there is no blue, something else is oxidized. So you need to use the colors that we talked about to determine what's oxidized and reduced, which will help you write your half reactions, because you'll need to write the half reactions that occur in each of the test tubes, each of those nail systems. Another thing to keep in mind is that you're going to need to identify the cathode and anode metals in each of the nail systems that you set up. So I said cathode and anode metals. So in this experiment, the cathode metal is the site of the reduction of oxygen, right? Oxygen is being reduced. The cathode is the site of reduction, and it's always a metal. In this experiment, the anode metal is the actual metal that is being oxidized. So whatever is being oxidized, it's going to be a metal in this experiment, and that is your anode metal. So part 2 of experiment 19 is an electrolytic cell. And so I'm going to go ahead and draw a diagram of this electrolytic cell that will be set up for part 2 of experiment 19. And so it just consists of a beaker. We can do our electrolytic cell in one container. So we have a beaker, and in that beaker we are going to put a green electroplating solution. So the solution is green, and the reason it's green is because it contains nickel 2+ ions. This electrolytic cell also needs to contain a cathode and an anode, and so these are two pieces of metal. So this is our nickel piece of metal here, and then we also have a piece of copper metal. And our electrolytic cell is hooked up to a power supply. A power supply is needed to drive the reaction in an electrolytic cell. So in this case, here's our power supply, and our power supply has a positive terminal and a negative terminal. And the negative terminal is going to be attached to copper. We're going to force electrons into copper, and then the positive terminal is attached to nickel. We're going to pull electrons from nickel. And that's what we're going to see in our anode and cathode reactions. So our nickel is going to be oxidized to nickel 2+, and we're going to force electrons into copper, and those electrons will attract nickel 2+ ions. So our anode reaction is the oxidation reaction, and as I mentioned, this is the oxidation of nickel solid going to nickel 2+, plus 2 electrons. So the cathode is the reduction reaction, and that is where we have electrons that are forced into copper. They're going to attract the nickel 2+ and become nickel solid. So what happens is we have electroplating of nickel solid on the copper metal. So there's going to be a coating of nickel solid on the copper metal. So we're going to be interested in calculating the amount of nickel solid that is created on the copper. So we're going to look at that calculation next. And so this is for the calculation of the theoretical mass of nickel plated on the copper. So we're going to run our cell at a certain number of amps, between 0.4 and 0.5 amps. And an amp is equal to a coulomb of charge running through our cell per second. So we'll take that value of amps in coulombs per second, and we can multiply it by the time the cell was run in seconds to give us coulombs. And then using Faraday's constant, which is 96,485 coulombs per every mole of electrons, we can then convert to moles of electrons. And then using stoichiometry that says that 2 moles of electrons are needed to produce nickel solid from nickel 2+, we can get the moles of nickel. And then, of course, we can multiply by the molar mass of nickel to get the mass of nickel that should be theoretically plated. So the molar mass of nickel is 58.69 grams per mole. So from this, we can see all the units that cancel out, right, using dimensional analysis. So we can cancel out our units. The seconds cancel out. The coulombs are going to cancel out. The moles of electrons cancel out. The moles of nickel cancel out. And we are left with grams of nickel. So doing this calculation with the data will give us the theoretical mass of nickel plated. So we can calculate the efficiency of the cell to see how well it worked. And that is done by taking the actual mass of the nickel plated on the copper, so that will be recorded as one of the data points, and divide it by the theoretical mass of nickel plated that we just went through, how to figure that out, and then times 100%, of course, to give us the percent efficiency of the cell.